All right, so we're going to talk about energy now for gravitation. And the reason we have to define a new potential energy is because we have an updated equation for the gravitational force. So if you remember, our old fashioned gravitational potential energy, well, we just said that if the force of gravity was equal to a downward mg, then that meant the gravitational potential energy was just going to be equal to the negative of the work done in moving the object, which we said just simplified to mgh, or mg delta h. And again, we set the 0 point to be the Earth's surface for this potential energy. But the issue with this is that now we're saying that this g is not constant anymore. Because we know that gravity actually follows an inverse square law. So that means that this whole expression for gravitational potential energy doesn't work at large scales. It's still incredibly useful when we're close to the surface of the Earth, and we'll continue to use MGH for that. But as we start to get far away, and on the planetary scale, we have to use the actual form of gravitational potential energy, which we can find just by integrating Newton's law. So in doing that, we see that the GMM over R squared turns into a GMM over R because the integral of 1 over x squared dx is just going to be equal to negative 1 over x plus c. And again, we define the 0 point of this energy to be at infinity because that allows us to get rid of this constant right here. So we pick up a negative sign. Nothing wrong with that. Energy can be negative because really with potential, we're looking at differences. And it's really going to come in handy when we figure out what types of orbits occur based on the system's energy. So first, let's just look at a point particle example. So here we have a system of isolated spheres, and we want to calculate both the net force on the left sphere, and we want to find the total GPE of the system. So first, observe that, well, the left sphere, it's going to get attracted to the middle sphere. So we have a force of attraction caused by the 2m. And then also, we have a force of attraction to the 3m. And I made the 3m arrow smaller because even though the mass is bigger, the separation is double. So it's going to drop off like the inverse square law. And they are going in the same direction. If it was net force on the 2m middle sphere, we'd have to make sure to account for that subtraction. But we don't have to in this case. It's just going to add. So the net force in this case, it's just going to be just the sum of the two forces. And both of these are just GMM over R squared. So just making sure we get it right for each of them. Well, we have the left mass is M, and it gets attracted to the 2m at a distance of L over 2 quantity squared. And then we have the mass M being attracted to the 3m, a distance of L away. So we're going to get GM squared over L squared as our unit. But for the first term, we see that we have a 2 on top, but then dividing by the 2 squared on bottom gets us an 8 for the number in front, and then we get a 3, so this simplifies to 11 GM squared over L squared. And that's our answer for the first part. Then moving down for the total gravitational potential energy of the system, it's important to note that U of a system is equal to the sum of all the U's of the unique pairs of particles. Because potential energy is always between two objects. So here we just need to see how many pairs of objects have an energy associated with them. So here, notice we have three particles. So we could find the energy between 1 and 2. We could find the energy between 1 and 3. Or we could find the energy between 2 and 3. And we're not double counting. So 1 and 2 is the same energy as 2 and 1. So we are just adding the pairs of energies. And that's just given by the negative GM over L formula. So first, for 1 and 2, we have, of course, negative G times the mass of M being attracted to a mass of 2M, and the distance between those two are L over 2. And then we have an M being attracted to a 3M, a distance of L away. And then we have a mass 2M being attracted to a mass 3M, a distance of L over 2 away. And after adding all of these together, we are going to get a GM squared over L. Our first numerator is going to be 4, then we have a 3, then we have a 12. So 4 plus 3 plus 12 is going to be negative 19 GM squared over L as our total potential energy. Now for a slightly more complicated system. 4 spheres of mass m are assembled into a square of side length L. Calculate the total potential energy of the system. So once again, the total potential energy of a system is just going to be equal to the sum of all of the potential energy pairs. So now we just got to figure out how many pairs we can form. If you know a bit of combinations, you could just say that 4 choose 2 is going to be 6, or just start counting. So first, I'm going to go through all the types of pairings we can make. So first, I can draw these 4 purple lines, which I'm going to call the adjacent masses. So all of these share a side length. So there's 4 of those pairings. But also, I could do some pairings on the diagonal. So also, I could pair the far masses with one another. So I also get 2 pairings from the diagonal. And this is a common issue in solving this problem, is forgetting about those diagonal pairings or putting in a wrong value. So now we can just apply the formula. So for the 4 that are adjacent, this one's pretty straightforward. We just get a negative G m squared over L. Because both masses are m, they're separated by L. So that's for each of the purple connections. And then for the blue line, so we have 2 of those. And then it's still going to be a negative GM squared. But then we got to figure out what L is. So if we just draw a little picture here on one of the diagonals, we are just dealing with a square. So if I think about it, if I want the distance between the 2 corners of a square, well, that's this hypotenuse right here. So if this is L and this is L, well, by the Pythagorean theorem, this is going to be L square root of 2. So that means L root 2 actually goes in our denominator. So it should make sense because it is going to be farther. Corner to corner is farther than side to side. So then we can just factor out the negative GM squared over L. And we get a 4 plus 2 divided by square root of 2. And working that out, we get gm squared over L times 4 plus, rationalizing, we actually just get square root of 2. And that is our final answer, or if you want to write it all as one fraction, we get negative 4 plus square root of 2 times gm squared, all divided by L. And that's our total potential energy of the system. So notice, forgetting that square root of 2 is a very common misconception there. All right, so next we're going to do a energy conservation question. So this is going to look very similar to what we've done with just the old MGH energy, except now, since we're dealing with things on the planetary scale, we have to use the new updated definition of our GPE. So, classic question, right? We got a rock, it's placed far above the Earth's surface, and we drop it a certain distance and want to figure out the impact velocity. So, it would be tempting just to say that U is getting turned into K, and then we say that mgh equals 1/2 mv squared. So V is square root 2gh, which would be square root of 4gre because we're 2 re's above the surface. This is actually going to give us a wrong answer because it assumes that g is constant. So definitely do not just apply mgh, because again, the gravitational force is not constant due to the inverse square law. So let's get rid of all this. So let's see how we actually have to do it. So we're gonna set this to be our initial state, and we're gonna set this to be the final state. So we're starting right when we drop the rock, and we're ending right when we're about to hit Earth's surface. So even though the energies have changed, it is just going to be the same old fact that the sum of the energies remains constant. But also we are at rest at the top. So our first kinetic energy term is 0. And then our new expression for potential energy is just GMM divided by R. And we'll plug those values in the next step. KE is still 1/2 mv squared. And then we have a different R value to put in here. Okay, so the biggest issue with this problem comes from deciding what R should be. So a common error is saying you have no potential energy at this final state, so we cancel it. And that's not right either, because we did not define the 0 potential energy point to be at the surface. We designed it to be all the way out at infinity where there's no attraction at all. So again, this R is distance from the center of the planet. So we have to account for that. So first, we get negative GM over how far away am I from the center to start? Well, I'm R to get to the surface, so that's R. But then I have to go up another 2R to get to the top. So it's actually 3R that goes in the bottom. Or you could think of it as R plus H. And then at the bottom, it's not 0, because it's only 0 if the R is infinity, but it's clearly not infinity. So how far are we from the center of the planet at the bottom? Well, it's just going to be R. So now we can see that we are going to get a cancellation of all the little m's, so the rock's mass, of course, doesn't matter. And then after adding the energies to both sides, we get 1/2 VF squared is equal to 3/3 plus minus 1/3 gets 2 GME divided by 3RE. So then solving gets us a final velocity of square root of 4/3 GME divided by RE. And if we also use the fact that little g is equal to gm over r squared, we could also show that this answer can be written as the square root of 4/3 g times re. And notice that you would get just a 4 there if we applied the old MGH definition. So we definitely have to do it this way, or else we'll get a wrong answer. Another application is escape velocity. So to escape means that your object is allowed to reach a distance infinitely far away from a planet. So if you just have a planet and something that's orbiting it, well, that's some energy level that requires. And it takes more energy to reach farther and farther away places, but it turns out that there's a certain amount of energy you can have that allows you to orbit infinitely far away, or escape. So why does this occur when you have enough kinetic energy to stop at a point infinitely far away? Well, energy of the system is equal to kinetic plus potential. So we're going to say the energy at infinity is equal to the kinetic energy you have at infinity plus the potential energy you have at infinity. So we're saying that no matter what is happening with your system, the potential energy at infinity is 0, because that's what we define it to be. So you have that the energy is just at infinity, is just going to be equal to the kinetic energy at infinity. And again, realize that kinetic energy is 1/2 mv squared, so it can't be negative. So that means that your energy must be a positive value to escape. And when the energy is equal to 0, that's your cutoff point of first being able to escape. So if your energy of the system is 0, you can just barely escape and stop when you're all the way out there. But if it's greater than 0, you get to infinity and still have some velocity left to spare, if you want to think of it that way. So let's derive an expression for escape velocity. So all that says is that, well, the total energy is equal to 0 when we're able to escape. So it's not helpful to use the final state here because both energies are 0. So we know that since energy is conserved, this means that kinetic at the start plus potential at the start must also sum to 0. Well, kinetic energy, we know that's just our typical 1/2 mv squared. And then our gravitational potential is gmm over r. And that has to be equal to 0. So then adding that to both sides, we get 1/2 mv squared equals gmm over r. Cancel the little m. So interestingly enough, it does not depend on the mass of the object. So escape velocity is purely a by-planet quantity. Because we get v escape is just square root of 2gm divided by r. And the m and the r are for the planet. So maybe we'll just indicate a little subscript of p for each of those. So notice it is entirely based on big G, which is universal, and the mass and radius of the planet. Nothing about the object is involved. So let's do that for the Earth, just to see. So the escape velocity on Earth is just going to be the square root of big G times Earth's mass. Oh, I missed a 2 there. I'll add it in. 2 times Earth, big G, times Earth's mass. 5.97 times 10 to the 24. Divided by the Earth's radius. And if we do that, just to see how much it is to escape from Earth, it's about 11,200 meters per second, which is 11.2 kilometers per second. And that's without air. So in reality, air is going to take some energy as well and do some work on the system. But in a planet with no atmosphere, if you launch straight up in an Earth without air, 11.2 kilometers per second, you will escape. All right, let Earth's velocity of escape be VE. What velocity is required to escape from a planet twice as massive? So again, anytime we got these ratio questions, you got to write the base formula down. So we know that V escape is equal to square root of 2g mass of the planet divided by r of the planet. So assuming Earth's radius, the radius of the new planet is the same, what velocity is required? Well, we could do this with the whole ratio approach. So we could do some sort of a ratio that looks like this, where V new divided by V Earth, I'll use capital, is equal to square root 2gm new, which is 2 times the Earth's mass, divided by r, divided by square root of 2gme divided by r8. We could do the whole ratio approach, and you'll see a lot of stuff does in fact cancel. So Earth's mass cancels, big G cancels, the 2 cancels, and the 1 over RE's cancel, giving us V new divided by VE is just equal to square root of 2, meaning the new velocity is just square root of 2 times the escape velocity from Earth. But again, I think the ratio is a bit overkill for this result. So again, just realize that escape velocity is proportional to square root of the planet mass. So if you're doubling the thing inside the square root, you're multiplying the entire expression by square root 2. All right. Now some important results are relating to circular orbits. So first, we're just showing that if you're a planet of mass little m in a circular orbit of radius r, or in a star of mass big M, total energy of the system is given by negative gmm over 2r, which is also just 1/2 of the potential energy. So, if we're asked about the total energy of the system, total energy is always just going to be equal to kinetic plus potential. Kinetic energy of the planet is 1/2 times mv squared. And then the potential energy is negative gmm divided by r. And that is not in the form that we wanted. So we'll have to remove this v. And if we recall, we are given the fact that it is a circular orbit. So circular orbit, which means that we're allowed to use circular motion ideas. So we also know that the centripetal force is being supplied by the gravitational force to keep it in orbit. So we know that mv squared over r for the planet has to be equal to gmm over r squared. And that tells us that v squared is equal to gm divided by r. So now we can replace v squared with gm over r and get 1/2 m times gm over r minus gmm over r. And notice that now these are like terms. We have a half of gmm over r, and we're subtracting 2/2 of gmm over r. So we are just going to get the desired result of negative gmm over 2r, which is equal to 1/2 of the potential energy. Because again, realize that if we just factor out the 1/2, we have the formula for potential energy. Because we just have a 1/2 times the negative gmo over r. Then let's also show that k is equal to negative 1/2 u. So doing this directly would work as well, but also just don't forget the fact that we just proved what energy was equal to. So we have energy equals k plus u. We also showed that total energy is equal to 1/2 of u. So thus, k is equal to minus 1/2 u. So realize we could use the other part to make this proof quite simple. Or you could go back up here and see that if this term right here is u, this term right here is negative 1/2 of u. You could do that as well. And lastly, we'll just do a work example. So suppose a satellite of mass m is orbiting a planet of mass big M in a circle of radius r. How much work is required to bring a satellite into a farther orbit? So let's just get a picture here just to get an understanding of what's happening. All right, so let's say we have a planet that's orbiting, and we have two different radii. So we're saying originally it's going to orbit in this small orbit r. And then we want to figure out how much energy it takes to get it to orbit in this big orbit of 4r. So this is definitely going to require energy because if you have a larger orbit, you're allowed to reach farther locations. So that definitely takes energy because currently it can only reach close locations, but we want it to reach far locations. So that definitely takes energy. So there's a couple ways of doing this. I'll do it the direct approach. So it says how much work. So I will use the direct formula for work. That says work is equal to the integral of f dot dr. And for this, the force required is just going to be opposing the gravitational force. So if we're going from a close orbit to a far orbit, we have to beat the gravitational force in order to do that. So it's just going to be the negative of the integral of the gravitational force dotted with dr. Because we're going against it. And then we can work out the definition of work. So it's just going to be gravitational force times dr times cosine of the angle between the gravitational force and the displacement. And well, gravitational force is trying to take us into the center, and we're going away from the center. So those are anti-parallel. So we're just going to be integrating the gravitational force with respect to the r vector. So now we can go up and just evaluate it. So work is going to be the integral from r to 4r of gmm divided by little r squared times dr. And notice that everything that's not r is constant, so gmm gets pulled out in front. And then we're just integrating 1 over r, or 1 over r squared, which works to negative 1 over r. And we're evaluating that from r to 4r. So we get gmm times negative 1 over 4r plus 1 over r, which is equal to 3/4 gmm over r. Alternatively, you could have just found this answer by taking the difference in potential energies between the two orbits and reason that that's the amount of energy it took to get you into that new orbit. But again, this is just showing that the integral definition of work still applies even when dealing with orbits. It's just a new force we have. And that's about it for our energy problems.